Hello, for the second problem for week 6B, I chose problem number 12. This is the light shining on a diffraction grating has a wavelength of 497 nanometers in a vacuum. The grating produces a second order bright fringe whose position is defined by an angle of 8.21 degrees. How many lines per centimeter does this grating have? So for second order, I have this demonstration here. Here's our slit in the middle, and then here's our angle, and this is our equation, and our equation is, I'll go ahead and explain, this is the wavelength of light, and its SI units is meters, which is m. It's the distance between the 2 points on the adjacent waves, so it's just right here, the first wave. And then m is the ordered number of dark fringe. It's the label of specific dark fringe. Its SI units is 0. Then sine is the ratio of opposite divided by hypotenuse of a right triangle. Its SI units is unitless. And then theta is the measure of an angle. SI units is in degrees. D is distance, and then its SI units is meters also with an m. And then it's a measure from one point to another. Right here when we're looking at these slits. So for this problem, how many lines per centimeter does the grating have? So we're looking at the grating, and so we want to be able to see, first of all, we have to find distance, and then we worry about the lines per centimeter later. So you can see this would be my M1, this would be my M2. This is my distance right in here between these two slits, or between the two fringes. And then this is my theta, this is the angle that it makes, and then this is my wavelength, because we have one wave going right there. So this is our equation. And I just moved d over here in order to get distance by itself. So I did. And then after that, once I had d by itself, I divided by sine theta in order to get d by itself. So the sines cancel out, and then you get m times wavelength over sine theta. So that's this completed formula right here. And I just fill in m. I have 2 fringes. So m equals 2 times 4.97 times 10 to the negative 7, which is wavelength. And then and that was figured out because we have to go from nanometers to meters, and that changes it to times 10 to the negative 7. And then sine, or divided by sine, 8.21 degrees equals 9.94 times 10 to the negative 7 over 0.143. And then this distance equals 6.96 times 10 to the negative 9 meters. And then just to go back to this, we were given nanometers, so that's what I converted it to here. And then I converted it to meters here. And then since we're at meters here, we can just plug this in because we already have our meters. So our distance, we know this distance right here, but we want to know how many lines per centimeter does the grating have. So we want lines per centimeter, but right now we have meters. So I did 1 line over meters, which is our distance. So that equals 1 over our number from right here, 6.96 times 10 to the negative 9 meters. And that equals 1.437 times 10 to the 5 lines per meter, but we don't want lines, we want meters. So we multiply times 1 meter to cancel these meters out, and then divide by 100 centimeters to be able to get 1,400 lines divided by 1 centimeter. So in 1 centimeter, there's 1,400 lines. And that was correct up here.